Hi, everyone, and welcome to our online series of machine control system course. And I welcome you all to our last and final chapter of our course, in which we'll be studying how to design a system via root locus, right? So, this is the final chapter, and I congratulate all of you that you make it so far to the end of this course, and I hope you enjoyed this course. So, in the last lecture, we have already discussed the fundamentals of root locus. What is a root locus, and what are the methods by which you can draw root locus by various techniques? And then we further move toward one of the techniques or approaches that can be used to find the root locus of control system, which was root locus by sketching. For sketching techniques, we have studied rule rules, including rule number one, rule number two, and onwards to rule number six, and some of the various observations which we noted in the final lecture. So, if now you are able to draw a root locus or understand how a root locus is drawn, so that's a very good sign that you might understand how we can design a system using root locus. So if you have any problems or you have any questions regarding root locus design, root locus sketch, then you can always revisit the lecture in which we have studied the root locus and discussed its technique. And you can always come back to this lecture and take it if you have any issues with that. So yeah, let's begin with the question which I left you with in the last class, and which was yeah, so I gave you an assignment to think that um, uh, and that what would happen to a system if I add additional poles, right, and additional zeros to it, right? So we had a control system, or you can say a plant function, in which there were two poles at -1 and -10, and we plotted root locus in the last class if we have already done that. So now I gave you the assignment and a thinking assignment in which you have to revisit that. If I add an additional pole to the system, an additional zero system, what the impact it would bring. So yeah, if you haven't figured it out yet, I will give you a little time to think about it and draw the patterns so that you could indulge with the process and you could grasp it more accurately. So if you haven't done that so far, so feel free to pause the video and do that, solve that out. And for both of these uh, plant functions, modified plant functions, draw the root locus and then continue in the video. All right. So the answer to the question is, if I add an additional pole to the system, which is actually at origin, so there would be an additional pole here, somewhere here. And if I have this pole here, then there would be straight line passing through these both, and one of root locus would be going upwards and one would be going like downwards, like exactly this line would be moved to somewhat here, and this root would be going towards zero at infinity to you. So in a general perspective, we can see that if I added an additional pole to the system, so the root locus moved towards the right. So this whole part shifted to the right of the system. So that is the observation which I wanted you to make, and you can also do that thing for the zeros, and the answer to this would be in general. So not always necessary, but in general we can say that if I add an additional zeros to the system, the root look it would impact the root locus to move towards the left, and if I add an additional pole, it would shift the root locus towards the right, as I have demonstrated in just now, and you will be seeing that thing again in the upcoming examples. So be very familiar with this transfer function example. I have deliberately chosen this plant function because I will be using the same function for the further demonstrating and design, and I'll be using this additional pole case demonstrate. So you will also see that this root locus would be shifted to the right. So if you have any questions, you can always ask me in my email, or you can personally contact me. Or yeah, so let's move forward. So now we are about to design the control system via root locus method. Yeah, so it's always necessary to note that we already know how to design a basic fundamental control system using values of zeta and omega naught. And once we have figured it out, we can form a second order transfer function, and we can generate its you can say an equivalent plant function. So now we are using the same thing, that is to design a control system, but now we are using a root locus technique. So the step one to design a control system using root locus would be number one, that collect all the required specifications and translate them into a design point in the complex plane to meet the desired specification. So there are two key terms here, which is the specification. So what is this specification? Number one, and translate them into a design point. So what is a design point? So actually, this specification and design point are actually near most the same thing, but the specification is basically given to you by a customer or a consumer. You can say it will specify you that I want my system to behave that much stable and that much uh, it could define the characteristics in terms of zeta and omega. And let's say if we talk about at least a second order system, so the specification will be given to you in terms of zeta and omega n, right? uh, Considering it's a second order transfer function, so that you will translate those specification into a point, right? So we'll discuss that how we're going to achieve that. But in if we convert that specification into a design point, both this design point and specification will be equivalent to each other, which means that your design point will be an equivalent representation of your given specification. So how can we do that? Let's say, for example, we have been given an specification where we want when our customer wants us to design a system with um, omega naught equals 2.5 radians per second and zeta equals to zero point 0.7 0.707. So of course we can clearly see that here, that this is an underdamped, right? If I'm not wrong. Of course, that's no point of being wrong here. Of course, this is less than 1, and we can see that this is less than 1. It's an underdamped system. Of course, we want an underdamped system with this much natural oscillating frequency. So our dominant poles can be given as, the roots of the equation we derive before. We call them m in chapter 3, and we drive them equals to sigma plus j omega d, right? So this was our point, or we can say this would be our design point. But now we have to figure out the values of uh, these sigma and omega d. So we can find out by using the derivations. If you revisit chapter number 3, so we have already derived this expression. You can always check it from there. This was equals to omega naught zeta, and this was equals to 1 minus uh, zeta square. So you can substitute these values of omega naught and zeta here, and you can find the values of omega sigma and omega d here. And once you find this value, you can substitute it in such a way which would be your design point. So now your design point will represent the specification given to you, right? So if you say specification or you say design point, they actually means the same, right? But your design point would be a representation of your specification on your S-plane. To be accurate, you can say that. Now, once we have figured out the specification and the design point of the system of the control, then we have to move to the next step, which is to sketch the root locus, of course, and then select or adjust the values of control parameters. All right, so there are parameters. In the last previous lectures, we have seen that we added an additional controller in the forward loop with the main plant function, if you remember, right? And that controller have some parameters. Let's say, for example, we started with a simple controller, which was a proportional controller. So it has a simple value k, which was gain. So we adjust that value, whatever the values or the parameters which are in your controller transfer function. You have to choose values or select values or adjust values, whatever you want to say, in such a way that the root locus should pass through your desired design point. That's really interesting. So now design point would be visible on your S-plane, and you want to customize your root locus to pass through that particular design point, and that's the point. So how could we do that? If a plant function is fixed and it has fixed amount of zeros and poles, so its root locus can't change. But of course you can change the controller and its transfer function, sorry. So of course the transfer function of the controller could be manipulated in such a way that the final root locus of the system is plotted in such a way that it passes through your design point, right? So of course, I made myself clear. But if you haven't understand that, let's move to an example, and I'll demonstrate it, what I mean by that. So let's start with a proportional controller. Let's say I have a plant function, and I choose a proportional control in the feedback in the forward path with that plant function, and I want to control. I want my system. I want to design a system which passes through my, in which the root locus passes through my design point. So let's see. For example, we have a plant function which is quite familiar, and I gave that exact um, plant function to you in in your homework thinking assignment, in which you have to reflect what you think about adding poles and zeros. So this is exactly the same transfer function, and now we have used a controller k, which is the proportional controller, and we want to set the values of k in such a way that our design point, that our root locus passes through our design point. So let's see if this proportional controller is able to do that or not. Let's see. So let's draw let's go for the first step of our control system design via root locus. So what was the first step? It was finding out the design point using the specification. So let's say if we have the similar conditions, so we have the same 2.5 and 0.707, which was your underdamped system, and we have the same design point right here for simplicity because we already covered that. So now we have been given a design specification, and we have fortunately have find out the design point, and we are moving to the next step in which we will be plotting its root locus. All right, so this was your root locus which was given to you, and you can easily figure out how you draw this root locus. And I guess that would be unnecessary if I go towards the discussion how you draw this root locus. So if you have any confusion regarding that, you feel free to watch the previous lecture, that how I use rule number 3 and rule number 4 to sketch this. asymptote based uh, root locus in which one angle is pi by 2 and another is minus pi by 2. We have seen a similar example in the last lecture. So all right, so I have plotted this plant function, or the culminated cascaded plant function. If I multiply k with this whole function, so it would be 10 times k and the whole value, and I draw its root locus, it would be like that. But now you can see that it's clearly visible that a design point is not passing through a root locus. Or you can say the you can simply say that root locus is not passing through the design point, which is p, and this design specification cannot be met, right? So in this using proportional controller, our design specification cannot be met. So if you try to achieve the design using a proportional controller for the same plant function, I'm sorry, you cannot achieve your design specification using a simple proportional controller, right? So now let's move forward and think about what else we can do. And what could be the disadvantages of using a proportional controller? Number one is very specific, that you want to control a system, and now since your control is not meeting your design specification, so I think there is no point in having such controller. So of course the disadvantages would be that we cannot meet the general closed loop specification, right? So there is no control, so there is no point in having a control block before the plant function which does not achieve the purpose, which is to have a to satisfy the design specification, right? So this is number one advantage. And number two disadvantage um, is that if you use a proportional controller, right, so the steady state error gets smaller as the gain is increased, right? But for high values of k, so you know, if you recall your table in which we have use different step inputs, ramp and parabolic input against different types of systems. So we have seen that if the system type is 0, then we will get a steady state error to a step input, and if type 1, we'll get a steady state error to ramp input. And by saying all this, we can conclude that this steady state error gets smaller as the gain is increased, right? So you want to increase the value of gain so that the error reduces. So if you remember, the value of this k, it was inversely proportional to the error. So you want to make this value higher as possible to reduce the error. But simultaneously, we have already discussed that for higher values of k, this may induce instability to the system, so which might not be a viable case. So this system not only fails to control the block, but also have a very practically very high error due to very not having a, you can say, a selectivity issue for k, which you can say that you cannot even increase the value of k to a level that it becomes unstable, and cannot reduce the value of k such that the error becomes too high. So it's like a catastrophe, you can say. So this system do not have a practical application to this plant function. So let's move forward. All right, so let's think about some new controller which could satisfy our design point without hitting a very high proportional gain, right? So now we're not interested for a high proportional gain k to be cascaded with our plant function, but now we want to find some other uh, controller function to manipulate our whole forward path. So yeah, let's think about it. Right. So of course you don't know, but yeah, let's try for a new type of controller which is called the integral controller. So we know what is an integral part, right? So in frequency domain, if you remember, integral what was 1 upon s, right? So an additional part, integral controller, what we added here. So it's a simple controller. The same situation and same examples are present here. Just the only difference is I added s in the denominator. You know that 1 upon s is your integral. We discussed this in our when we studied the general structure of a transfer function, in which we said that we have a gain multiplying with the plant input output upon input and divided by the integral, or you can say the number of integrals present there. So this is 1 upon s is your integral control, right? And we can say that in frequency domain, the integration or integral is equivalent to division by s. So we picked a function which is k upon s. So k is some constant number, and if this is not a proportional control, so yeah, my bad. You can change it to um, your integral control, and this would be ki, let's say. So this gain, you can say that this is a integral control gain ki. For simplicity, you can say that. And let's plot this system. All right, so this is exactly the system which I gave you to plot when you add an additional pole at s equals to 0, right? So you can see the impact here, that this additional pole is added here, and this shifted the whole root locus to the right. So you can see the difference. If you added this k upon s, the root locus changes. So that is like quite a good estimate, that if you change the values of gc or the controls um, uh, controller functions, so you can manipulate the root locus. So now we can manipulate the root locus, but the problem is still it does not passes through our point p. So we can make two observations here, that the root locus is pulled to the right, which was obvious, and we have done it before, so it's not new for us. But the new part is, but again, our integral control has failed to meet the design specification because the root locus does not pass through point P. And we can say that integral controls also fail to meet the design specification, or fail to pass through the design point. Why? So that's an interesting question. Why our integral and proportional controller both failed? What is the reason why we are failing? So take a moment and pause the video and think about it, and think the ways, what is the prime factor or the expression or the mathematical term which is responsible for not not able to meet the design specification, and what could be manipulated further to meet this design specification. So feel free to pause the video and we'll continue. All right. So in this case, you can see that both proportional and integral controllers are completely characterized by GS. What does that mean is that all our controller functions does not have any information regarding the design point. So design point is something which you derived before you plot the root locus, but none of the parameter which is mentioned in design point is part of this controller. So how this controller would know that it wants to pass through that point, right? So only information it has is some fixed parameters, maybe a gain, maybe an integrator, and it is amalgamated with the, or cascaded with the plant features. So it does have just only characterized by the proportional and integral controller are only characterized by the type of system they are subjected to, and they do not have any information regarding the design point which you uh, secretly wanted to predict. But that's not the case. It's not an intelligent controller. So you want yeah, what could be the next case if you imagine? So maybe you want a controller which do have some information regarding the design point. So it does involve some features which is part of some design points, and then in that way this GC or the controller transfer function would know where to pass this root locus from, such that this passes through point P and it satisfy the point P satisfies the root locus and it meets the design requirement. All right, so then think differently. All right, so let's try this style of having T. All right, and all right, so let's use our brain 100% and uh, we finally know that. Let's try something which is the control of proportional and integral combined together. So we call it PI, or the proportional integral control. So it's quite obvious from the name that we sum up all both of the controllers and we form a new controller. So let's try this on the new type of controller. But before that, let's simplify the expression for the PI control. And we can see that this is the Kp is the proportional control and Ki upon S is the integral control, and we can simplify it by taking the LCM and then factorizing it, and then we can call Ki upon Kp as a single parameter, which is, let's say, alpha, and we can substitute that as a value, and we have this new control block here which involves kps, and this is the new parameter here. And of course we can use the same block function here as a control block, so this would be your pi control, and alpha represents here a controller's zero, right? So why it's a controller zero? Because of course this is the this is not the plant function, this is the controller transfer function. And the numerator, if you equate this whole numerator with zero and find the value of s, so you would get s equals to minus alpha, which would be the location of your controller's zero, right? So of course we know that if you equate the numerator with zero and we find the values of s, those values of s are called zeros, and of course this is not for the plant function, so this would be for controller and we can call it controller zero. So now we have a controller function which is not only characterized by plant function but also by the design specification. So this alpha would tell us how to meet our design specification. So using this we can satisfy the design specification. Right, so we must choose a controller zero in such a way that the closed loop design point is on the root locus or lies on the root locus, right? So we must choose this controller zero alpha value in such a way that the design point do lie on the root locus. And number two, and then we have another parameter kp, so we have to also adjust the values of kp to get the the required closed loop dominant pole. So this would help us get the desired, you know that, right? So you can see that in it, like proportional gain, it can also manipulate the zeros. So we want it can also manipulate the zeros and the poles and the stability of the system. So also we can control the stability and the response of the function using the value of kp, as demonstrated in the lecture before this, in which we studied the root locus sketch and we manipulated the values of k, and the root moved towards some point and changing the nature of the system from stability to instability and different types of characteristics, right? So no need to go into detail further about that. So let's see an example. So it's an easy example, and in which we have a simple transfer function, 10 upon s plus 10. So we have just one pole at minus 10 and there is no zero. So we have used a GC, or you can say a controller, plant controller, which is actually your PI controller. You have already derived that expression before. And the first step would obviously be to find out the specification. So this would be your specification, let's say, and we find out the values of alpha and omega d, and we have this point, design point P here, which would be your closed loop design point. And then we will sketch the root locus in step 2. So now we know that if we multiply these two, so we would have one pole at S. So all right, so GC gets multiplied with GS, right? These are both part of the forward path gain and they are cascaded together, so these would both would get multiplied, and we will get s into s plus 10 in the denominator, which indicates that one pole is at s equals to 0 and one is at s equals to minus 10, right? So we have this minus 10 and minus, 0 location poles. So one pole is at location 0 and one at minus 10, and simply now we have an additional controller 0. Remember that? So we have a controller 0 at a somewhere, right? Somewhere here, right? All right, so do not confuse and with this alpha and this a. So this is actually your a and this is your alpha, which is indicates this is your sigma, basically, which represents your design point, right? So now you want to choose the value of a, or this a you can say, right, or alpha, you can say alpha or a are the same, and this is actually the sigma. And unfortunately the symbols are the same, but I should have changed that. But yeah, this alpha and this a are same, but this is sigma, and you want to choose the point p in such a way, you want to choose the value of a in such a way that this root locus should pass through this point. So now you want to use an analytical technique and remember the rule number 4 of root locus sketch, in which we study how to verify if a point passes through root locus. So we discussed that the if a point if a point come on if a point passes through your um, root locus, then you can say that if you substitute the values of that point into its transfer function, right, the forward path gain. So you can always say that sum of the k times gs would have been equals to 1 magnitude plus minus 180 degrees, right? So this was so this is your magnitude sign, right? So, and this is actually your 1. This was your um, gain criteria, and this was your angle criteria, if you remember. So we have like drawn all the equations, and we have already figured out these values before in the last lecture. So feel free to revisit that lecture or the slide, whatever you feel comfortable with. And will use the same structure here, in which we'll use rule number 4. So start with angle criteria. So we know that whatever the angle which were present in the poles were added and zeros were subtracted. So I added the angles of the pole P1 PZ. So this, let's say this was P1 and this was P2. So I added this angle and subtracted the angle of the zeros because it was on the opposite side of the denominator, right, numerator. And I added these with the different sign polarity, and this should be equals to 180 degrees, right, as per our angle criteria. So let's first find out the value of delta P1 using general geometry. So you can always see that what are the angles, and you know the ratio of perpendicular to base is your tangent. So you can always figure out for P1, which would be mm, which would be so for P1 this would be like 180 minus this angle, right? 180 minus this angle would be equals to P1, and this angle is equals to WD minus alpha. And so you have find the tangent inverse here, and you will finally substitute the values of omega d, which you have the design point, right? So now your angle are decided through your design points. You can already see that. So P1 is not something random angle, it's a special angle which is a function of your design parameters. So it's quite interesting. So you put these values here and you find the values of P1, and likewise you can find the values of angle P2, in which you subtract 180 minus this. So we know that P2 is actually equals to 180 minus this angle, right? and this angle is actually equals to tangent inverse of WD minus this value, which is minus alpha minus 10, minus of minus 10. So you substitute that and you find the values of uh, angle P2, which is 106.5. And if you know these both values, you can substitute into the forward equation and you can find the respective value for delta Z, angle Z, which is 61.5. Now you have all the angles figured it out. You can find the values of uh, alpha A here. So you want to find out this A here, and you know that you can find the perpendicular over base ratio. This would be your perpendicular and this would be your base for A, right? And this length would be, you can sum up and solve it for A, and you can find the value of A, which was your actually your location of your controller 0 on the real axis would be at 21.8. So that means if you place a controller with controller 0 at 21.8, so in that case your root locus would be drawn in such a way that it would pass through your design points. So yeah, so that's quite interesting. So you manually put some features into your controller such that the controller and the plant function now collectively works together to satisfy your design specification. Yeah, that's the crisp of the idea, or your whole of the idea, right? So once we have the value of A, we can use the gain criteria, and by gain criteria we can find out, we still don't have some features find out, so we don't know the values of kp here right now. So what we can do is, using the gain criteria, we know that all the magnitudes in the numerator divides with the magnitudes with the denominator, and all those mathematical operations comes up equals to 1, which was your um, satisfy gain criterion, which the point satisfies the equation. So you can always check how can we arrive with this gain criteria. Take your moment, take your time to revisit the lecture and find out how this came through from your gains criteria. We have discussed the all derivation part there. So yeah, so you can find the value of k by sorting it for k, and now you want the values of p1, p2, and pz, and these are the magnitudes. Okay, and you can find out the values using distance formula, right? So we know this point, the y-axis of this point are 0, 0, 0, and these are actually the abscisses. And we have, for the design point, we have the complete location of pole. We can apply distance formula for vz, vp1, and vp2. So let's use distance formula, and I apply distance formula. You can solve it yourself, and these are the results of your distance formula. You can get it, and you substitute this value for the value of kp, and we have 1.84 as the value of your kp. And now we have the values of k, right, and the values of a, right? So we have the values of a here and the value of k here, so we can substitute back into your controller function. And by substituting that, now we have a completely defined controller, or a PI controller, which eventually is designed in such a way that it satisfy your design specification or design point, right? So it is designed in such a way that your root locus would pass through your design point. So in that way, it would have the same feature you were desiring, right? With all of the characteristics involved, right? So let's check how a controller using conventional method. How can we use the conventional method to design, right? So let's validate a result. So there, find out and let's find out that this uh, controller function with another technique, which is already known to us, which is not new to us, but just that we want to verify this result and validate this result, that either it's the same as we achieved from our conventional method using our general equation of second order system. So this would be our controller and this would be our plant function. So I'm using the PI controller here. So if these are PI controller, this would be cascaded and we have unity feedback. So let's simplify it. the whole transfer function for the closed loop ratio. So this is how we find the closed loop ratio g of s times gc upon 1 plus gc and gs, and we solve it out and we have a second order function like that. And now we can compare it with our standard second order equation, which was in terms of zeta and omega n, right, to find out these values of k and a. So like, yeah, this is an alternative method to use that. But yes, of course, if you use root locus design using root locus, then you must use that those sketching techniques and all of that stuff. But here, if you can also, of course, you can use, if you know that this controller would work on this sort of function, on this sort of plant function, then of course you can use this method as well. So, but yeah, if the question in the in exam would be for root locus, then you have to go for root locus technique. Otherwise, you can use both of them. So let's compare this denominator with this standard equation, characteristic equation type, and I can find the values of zeta and omega n from here. And I found fortunately the same values of k and a. So yeah, exactly. Our root locus design was validated using the conventional technique, and I found out the same transfer function which was present there. All right, so some more controllers. Um, so this was actually before going to more controllers. Um, this was actually the summary, or you can say the main idea how the design works, right? So this is not exactly we have discussed the overall control system design. No, this is just the starting of it, right? So I wanted to give a perspective of how you can always have step-by-step approach. You start with a proportional control and then PI control, and sometimes you want to go for PID control, right? Which would we be discussing superficially. So you can always go through it, and the main idea is to intelligently design this control function in such a way that it meets your uh, design specification or design point, right? So that's the core idea which is here um, preferred, or you can say that. So yeah, let's move towards the more controller types. Of course, we know the PI control, the basic controller we have, which we have just studied and discussed in detail. And the basic function is to improve the steady state error, right? So it increases the system type because we added an additional zero pole here. So it increases the system type, and error becomes zero for the particular inputs in such a way. And of course, the zero at minus ZC is small and negative. The active circuits are required. So this is for the electrical part. So we need to go for the active circuits. But yeah, but if some way we can, I guess, we can relate it with mechanical, how an active uh, loop would be there. But yeah, so that's the whole point, to improve the steady state error and do not change the value of Kp so high that you disturb the overall steady state error condition in such a way, right? So that's the whole idea of using a PI controller, and then you can use a lag controller, so you can always check these. And then PD controller would have a not a in this we would in this PI we would be using 1 upon S as additional pole here, and now we'll be using an additional 0 in the PD because S getting not divided but multiplied here. So it would have another features, and it will improve the transient response of the system. And if I collectively want to use the improve the steady stater as well as this improve the transients response, so I use PID controller, that is the active features of both, but that uses some other functions, which is that is your lead controller and lagging controller. So you can always search on the internet or the directories and your coursebook about these functions, but these are not uh, prime subject of our control design subject here for now, at least for this basic course. But you can always figure out, especially the PID one is quite interesting, and you can always check some interesting examples and the key characteristics you can read out. These This is just for your reference. So this is how we design a basic control system. This is the whole idea of the whole idea for the course, that once you establish the key concept of the stability and characteristics of a control system, you would be able to define or design something which is uh, something of caliber of you can say of design engineering, right? So yeah, that's it for this lecture, and keep in touch. Thank you.